So here's an interesting question. What's the number of ways to put n identical objects into some number sets? Okay, well, let's just work on it. One object into one set, there's only one way to do that. One object into two sets, there's only one way to do that, leave one of them empty. One object into three sets, and so on. Two objects, one way to put two into one set, and there are two ways to put two objects into one set. Three, and this is getting clunky with all these dots. 3 in the single set, 3 in one of the two sets, and 0 in the other. 2 and 1, 3, 0, 0, 2, 1, 0, and 1, 1, 1. Well, this gives us another formulation of the question. The number of ways to put n identical objects into m sets is also the number of ways to write the number n as a sum of at most m positive integers. All right, so let's do 4. 4, 4, 0, 3, 1, 2, 2, now 3 integers, 4, 0, 0, 4, 1, 0, 2, no, 3, sorry, that's not right, 4, 0, 0, 3, 1, 0, 2, 2, 0, 2, 1, 1. And all of these work with 4 sets, and one that doesn't work with 3 sets is 1, 1, 1, 1. Alright, so you get the pattern there, and you can probably work out 5, 6, 7 by yourself. What is, though, the number of ways to put in different objects into m sets? Well, one different object is no problem. There it is in one set. There it is in two different sets, and so on. Two different objects. They can go both into the same set when there's two sets, or they can each go into their own set. That's only two different ways. Alright, 3, we start getting a little bit more complicated. If there's two sets, we can put them all in one set, or we can put in another empty set, or we can put 2 in one and 1 in the other. Alright, but there's 3 different ways to do that. You could have B and then AC, or C and then AB. So there's 4 ways to do that instead of with identical objects. There was 2. Alright, and with 3 sets, we could again have them all in the same set. We could have 2 in one set and 1 in another, and there's 3 ways to do that, with an A here, a B here, or a C here, and the rest over there. Or we could have everybody in their own set. Alright, let's try 4. So we could have all 4 in the same set, and that's the only way to do it with one set. With 2 sets, all 4 in one and 0 in the other. 3 in one and 1 in the second, but there's 4 ways to do that. 2 in one and 2 in the second. And the number of ways to do that is the number of ways to choose 2 of these out of 4. 4 choose 2. For 3 sets, 4, 0, 0, only one way. 3, 1, 0, 4 ways. 2, 2, 0, 4 choose 2 ways. 2, 1, 1 again. 4 choose 2 ways because once we've picked these 2, we've picked the entire distribution. 5, we get a little bit interesting. 5 in 3 sets. Consider 2, 2, 1. 2 of these objects in one set, 2 in another set, and 1 more off by itself. How many ways are there to do this? I think that there's 5 ways to choose that, and then once that's chosen, there's 4 choose 2 ways to choose one of these, and the other is set. So I think that's it. But this is very fun to explore. I want to do that. A third problem that I love is the number of trees. All right. With 0 nodes, there are no, well, there's one tree, the tree with 0 nodes. For 1 node, there's 1 tree, there it is. For 2 nodes, there's 2 trees, or sorry, 1 tree, there it is. 3 nodes, 1 tree. All right, 4 nodes, you start getting more trees. 1, 2, 4 nodes can be strung on a tree like this. Oops. Or like this. So there's 2 different trees with 4 nodes. 5 nodes. I'm going to stop drawing the endpoints. So 1, 2, 3, 4, 5. There's a tree with 5 nodes. 1, 2, 3, 4, 5. There's a tree with 5 nodes. 1, 2, 3, 4, 5. There's a tree with 5 nodes. So 1, 2, 3 trees with 5 nodes. All right, 6 nodes. We can even think of these as numbers again, maybe. These look like zeros, right? And these look like ones. This looks like a 2. So this is a tree with 6 nodes. 1, 2, 3, 4, 5, 6. This is a tree with 6 nodes. 1, 2, 3, 4, 5, 6. This is a tree with 6 nodes. 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 Now, when we get into 7 nodes, when things start to get very weird, we have 7 nodes. What should this look like? Could either look like 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. These are different trees, the same sort of numbering. So this number system has failed us. That's what makes counting trees such a fascinating problem to me. It's hard to trust one's intuition about this.